and we are picking up where we left off in our 6.1 class notes on vectors. So right now we're looking at example 7. Find the unit vector in the direction of 3, 2 in both component form and as a linear combination of I and j. So I and j were our unit vectors in the horizontal and the vertical direction. So a unit vector is a vector with magnitude 1. So we're looking for some vector whose magnitude is 1, but in the same direction of 3, 2. So if I go ahead and call this vector v right now, I could sketch a quick graph. 1, 2, 3, 1, 2. It's going to look something like this. That'd be my vector v. That has a much longer magnitude than just 1. In fact, the magnitude of v is going to be the square root of 3 squared plus 2 squared, which is 9 plus 4 is 13. So I want my unit vector u to essentially be, well, instead of the square root of 13 units long, I want it to be 1 divided by the square root of 1/13 times these components. I want to shrink it down, essentially. I want to shrink it down. So its magnitude is 1, which means each of my horizontal and vertical components need to be shrunk down by 1 over its magnitude. So u is going to be 1 over the square root of 13 times 3, 2. So my unit vector u should be 3 over the square root of 13, 2 over the square root of 13. And that is in component form. And if you're still like, I don't know, how do we know that's a unit vector? We could just check real fast. We could check by taking the magnitude of u. So the magnitude of u is going to be the square root of quantity 3 over the square root of 13 squared plus 2 over the square root of 13 squared. And when I square both of those, the square root of 13 is just 13, but 3 squared is, that'd be 9/13 plus 4/13. Well, 9 plus 4 is 13, so this is the square root of 13/13, which is indeed 1. So it is a unit vector. So that's my component form. As a linear combination, right, I'm just going to say this is 3 divided by the square root of 13 times I, plus 2 over the square root of 13 times j. So that's our unit vector. Now what we're going to spend the rest of this video focusing on is velocity as a vector. So the velocity of a moving object is a vector because it has both speed and direction. So that speed is the magnitude, right? So speed is the magnitude of the velocity, and it is a scalar. Remember, a scalar is just a real number. So if Nikhil is flying a plane on a bearing of 140 degrees at 480 miles per hour, determine the component form of the velocity of the plane. So let's first draw a bearing of 140 degrees. So bearing is from true north. So there's 90 degrees plus another what will give me 140. So 140 minus 90 is 50 degrees. So really I'm looking at something like this, where this angle here, if I wanted to call it my direction angle, it's actually negative 50 degrees because I'm in quadrant 4 there. So again, we can say the direction angle is negative 50 degrees, or we could say it is, well, 360 minus 50 is 310, right, or 310. But since all I want is the component form of my velocity vector, so again, my vector v is the magnitude of v times cosine of its direction angle, sine, not cosine again, sine, come here, sine of its direction angle. And so for Nikhil, this is your velocity. 480 is the velocity. And since cosine of 310 is the same thing as cosine of negative 50, I'm just going to use negative 50. And I'm going to say his velocity vector is 480 times cosine of negative 50 degrees. That is the first component, the horizontal component, and the vertical component is 480 times sine of negative 50 degrees. And so that's what I have exactly. Punching that into your calculator. Let me grab mine real fast. Punching that into your calculator, you should get roughly 308.5 horizontally and negative 367.7 vertically. And so what does this mean as a velocity? Again, these are in miles per hour, right? So he is traveling 308.5 miles per hour to the right horizontally, and he is traveling 367.7 miles per hour south, right? Essentially negatively going down, right? So this negative gives us the direction, down instead of up. So that is the component form of the velocity of his plane. Example 9, let's do another velocity problem. So Lydia flies her plane on a bearing of 200 degrees at 350 miles per hour. So let's sketch that real fast. A bearing of 200 degrees. So again, bearing and direction angles are different. So there's 180 and then another, well, 180 plus 20 more would be 200. So this right here, if that's 200 degrees, right, I could say this little reference angle here is 20 degrees. And so in terms of 350 is her magnitude, miles per hour. So plane, we'll let that be P for the plane. The plane has 350 times cosine of its angle. So what is its angle? If I'm thinking direction angle theta, right? So angle theta, I'm coming over here. If that right there is 20 degrees reference angle, that means over here I've got 70, because 70 and 20 makes 90. So 180 plus 70, 180 plus 70 gives me 250 degrees is the theta direction angle. All right, so we can say cosine of 250 degrees, sine of 250 degrees is the plane's velocity vector. But then there's the wind, and the wind is blowing. Hang on, let me see if I can. Not what I wanted to do. I just want to change the color to blue. All right, let's move this back up. All right, the wind blows 60 miles an hour on a bearing of 110 degrees. So again, a bearing of 110, there's 90, it's going to be here, right, so this would be the wind. So if all of that is 110 minus 90, that means, again, this is going to be 20 degrees right there, because 90 and 20 is 110. So here, I'm going to be lazy, and I'm just going to call the direction angle negative 20 degrees. Rather than saying that's 360 minus 20 is 340 degrees, I could say that if I wanted to, but I'm just going to say the direction angle for my wind is negative 20 degrees. And the magnitude is 60, so that's going to be 60 times cosine of negative 20 degrees times sine of negative 20 degrees. Alrighty, so determine the actual speed and bearing of Lydia's plane. So what is happening? Let's draw another picture. So we'll just draw our whole big axes here. So Lydia is flying her plane this way, but the wind is blowing this way, right, at a much smaller, right? So if this is 60 magnitude, this is 350. And so what you have is the resultant, right? This wind is pushing the plane off course. So we are pushing the plane off course, and the resultant vector, r, right, so r is just equal to, well, the plane's velocity plus the wind's velocity. And that would be your resultant velocity vector. So whether this is in quadrant 3 or quadrant 4 really kind of depends on what this sums to. So exactly, you're going to get something like this. In the horizontal component, you're going to have 350 times cosine of 250 degrees. So 350 times cosine of 250 degrees plus 60 times cosine of negative 20 degrees, comma. Now for the vertical, you are going to have 350 sine of 250 degrees. 350 times sine of 250 degrees plus 60 times sine of negative 20 degrees. So that's what we have exactly. Grab your calculator and punch those numbers in, and what do we get? So if we punch those in, we should be getting approximately, this sums to like negative 63.325, comma. Ooh, so what quadrant am I in? If the x coordinate is negative, I'm still in quad 3. And then this is going to be negative as well. And in fact, it's going to be about negative 349.4136, right? So because I'm negative, negative, I'm in quadrant 3. That's going to be helpful when we're trying to figure out our angle, right? Because I need to find the actual speed and bearing. So the actual speed, how fast is the plane actually going? The engines are turning over at 350 miles an hour, but in fact, that wind is giving it a little bit of a push, and so the actual speed is the magnitude of the resultant vector. So I'm going to take the square root of, again, use your calculator, use exact values, this squared plus negative 349, negative 349.4136 squared. When we square root the square of each of the components, the actual speed is going to be about 355.1 miles per hour. So that's the actual speed. Notice it's going just a little bit faster, about 5 more miles per hour faster. Now to find the bearing, that's going to take a little bit more work. So to find the bearing, we have to think of a couple things. So first of all, if I were to just straight up take tangent inverse of this y value over this x value, negative over negative, think about this, if I do tangent inverse of negative 349 point blah, 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 all over negative 63.32 blah, 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 blah. If I do tangent inverse of that, that's the same thing as tangent inverse of, well, if they were both positive, right? 349.4 all over 63.3 da, 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 da. And that's going to give me something in quadrant 1. Yeah. So this right here is actually what I get for tangent inverse. It's going to give me a positive angle in quadrant 1, which is approximately 79.7 degrees, right? So that is, if I redraw this picture again, we've got our actual resultant vector, and then, assuming I can draw a straight line, right? This angle here is the same thing as that angle there, yeah? So what is my bearing? My bearing is going to be from true north. So I want to go 90 plus another 90, right, plus this much more. So there's 2 ways you can think about this. I'm going to say my bearing is actually 270 degrees. I'm going to go the full swoosh, 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 and then I'm going to subtract my blue, my 79, minus 79.7 degrees. So my true bearing is approximately, let me make sure there's a nice decimal there. My true bearing is approximately 190.3 degrees. 90.3 degrees. All right? And that's where we'll stop this video.